The kinematic approach to plastic analysis uses an energy balance to determine either the plastic load factor at collapse, lambda collapse, or the plastic moment required to resist collapse, MP. The energy balance is given by E dot equal to minus WE dot plus D dot subscript P equal to 0. The dots indicate rates of work or rates of energy change, where WE is the external work, that is the work being done by the loading, and dP is what we call the plastic dissipation, or sometimes known as the internal work. And this work occurs at the plastic hinges. In order for the energy to be balanced, this equation must sum to 0. An important aspect of this analysis is the consideration of deformations and displacements. Generally, the energy balance can be depicted in the following way. Firstly, we wish to identify the displacements caused by the externally applied loading. The first such displacement is underneath the horizontal load. We indicate this as lowercase delta subscript b h. The subscripts are due to the labelling of the various parts of the structure. So what this means is we've got a displacement occurring at point B in the structure, and the subscript h means that this is due to a horizontally applied load. The next displacement is delta C, V, and this is because the displacement is occurring at point C in the structure, and it is due to the vertically applied load. Now we need to consider the deformations associated with energy dissipation at plastic hinges. The first thing we do is we indicate the angles of deformation. In this case, we have theta 1 at location A, theta 2 and theta 3, theta 4 and theta 5. The values of these angles will be determined in subsequent videos, but it's sufficient to say that you need to indicate where these angles are only at the locations of plastic hinges. For this particular type of structure, we have decided that there is no plastic hinge forming at location B, so we do not need to calculate the angle of deformation there. Finally, we need to indicate the value of MP at the locations of all of the plastic hinges. In this case, we've assumed that MP is the same for all cross sections. So we have MP at A, MP at C, MP at D, and MP at E. In terms of the externally applied loads, the external work done by these loads is given by the magnitude of the loading times by its corresponding displacement. So for the vertical load, we have V times by delta C, V. And for the horizontally applied load, we have H times by D subscript B, H. For the plastic dissipation at the hinges, we simply sum up the plastic moment times by the rotation of the hinge at that location. So we have summation of MP times by theta I. To see how this method works in practice, we can use some simple examples. Consider the cantilever beam with a cross-section of MP, a length L, and applied loading of lambda times by W. The plastic collapse mechanism has a plastic hinge at the support and an angle of rotation of minus theta and a displacement of delta B V, where the locations are A and B. Firstly, the displacement can be calculated. Delta B comma V, that's simply equal to the length of the beam times by its rotation. Secondly, the external work done by the load, WE, has to equal the internal work done at the plastic hinges, or dP. The external work done by the load then is the applied loading times by the corresponding displacement, and the internal work done at the hinges is given by initially the moment MA times by minus theta. We retain this for the moment because we may wish to return to this equation to perform a static check. At plastic collapse, we say that lambda C is equal to, lambda C is multiplied again by the applied loading and the corresponding displacement, which we've now substituted as L theta. And crucially, because this is now at collapse, the moment MA becomes minus MP times by minus theta. We're using the minus sign because we need to make sure that the sign on the plastic collapse moment is the same as the sign of the angle of rotation. Then the plastic collapse load factor is given by NP over WL, or the plastic collapse moment is given by lambda C times by WL. The next example, consider the simply supported beam with a concentrated load at the center with a value of lambda W. Then at collapse, the collapse mechanism has the following form. We can calculate the angle of rotation at the center of the beam, where the plastic hinge occurs, by considering the angles at the end of the beam, which in this case are both minus theta. The angle then at the plastic hinge location is just the sum of these, which is 2 theta. The displacement under the applied loading is given by delta subscript B comma V. The displacement then can be calculated as L over 2 times by theta, and equating the external work done to the internal work done, we have lambda W dBV is equal to MB times by 2 theta. At collapse, then we have lambda C times by WL over 2 times theta, where we've now just substituted in for what dBV was, and this is equal to the plastic collapse moment times by 2 theta. The plastic collapse load factor then is given by 4 MP over WL, and the plastic collapse moment is given by WL lambda C over 4.